Hello, and welcome to your video on binary phase diagrams with two soluble elements. Before we go any further, you want to make sure that you are following along on the handout. You're going to see that there is a blank diagram in the upper right corner. You're going to want to follow along what we're doing and fill that in as we go. As we move along through the video, we're actually going to be steps that we take to fill in our diagram, and those steps are listed there for you. So at this point, you don't need to write notes and take things down. You just want to watch, listen, follow along, and start to develop your understanding of binary phase diagrams. Then summarize what you've learned so that you do start moving this into your long-term memory. All right, so what is a phase diagram for? Well, the phase diagram has a number of parts, but our main goal of the phase diagram is to help us out if we have a material that's made of two elements, and specifically two soluble elements in this case. And we're showing that we could be soluble as a liquid or a solid. And you might say, wait, how can we be soluble as a liquid and a solid? Because we learned, watching our saltwater demonstration, that if we have salt with solid water or ice, they are not soluble. Well, it turns out there's a very limited number of elements that are actually fully soluble, liquid or solid. Typically, it happens first in the molten state, but as they're cooling, they're actually able to replace one for one, perfectly interchangeably, atoms in the lattice structures. Copper and nickel is a great example of this because they have the same crystal structure. They're both face-centered cubic unit cells, and then critically, their radiuses, atomic radiuses, are the same. They also have the same electronegativity and valence electrons. So the first thing we want to do is talk about what's even the purpose of a phase diagram. And to orient ourselves to the phase diagram, let's notice on either the diagram on the left or the right that it's actually representing two different materials. So on the top, we see that we have material A, and we're representing the percent of weight that's material A. And then on the bottom, we have the percent of weight of material B. If we have a binary system where we're just mixing two materials together, if we have 50% material A in the mix, we must have 50% material B. If I have 75% material A, I must have 25% material B. And so you'll see on the top, our percentages go from right to left, and so on the bottom, they must go from left to right so that the percentages correspond with each other. We're going to do an example for an alloy that's 60% material A and 40% material B, so we immediately can represent our composition doing step one on your handout, and that's to draw a vertical line that represents your composition. We want to label the points, 60% and 40%, and the labels that we use are very important because they come up later in formulas, and we can see them there in our step one, but we're going to call the percent that is material A, P sub A, and the percent that is material B, P sub B. So hopefully we got our vertical line at about 60 and 40%. Unfortunately, there's not a lot of tick marks on our axes. Now, if we were 100% material A, we would actually know our melting point. Or if we were 100% material B, we would know our melting point. But as we start mixing materials, we actually start changing where the melting point is at. And if we look on the left diagram, we've actually highlighted the Liquidus line in green. And that Liquidus line, which connects our two melting points, that's now showing the change in where our material starts transitioning from liquid to solid based on the composition. So we can see the closer we are to material B, we're at a higher temperature. The closer we are to material A, we're at a lower temperature. As we change our composition, we change where we transition from liquid to solid. But we don't immediately transition to solid like we would if we were all material A or all material B. And so we must mark the solidus. This is the line where we would transition 100% into solid, and you can see it's lower at material A and again higher at material B. But in between the liquidus and solidus, we actually have our material would be partially solidified or partially liquefied. and we'd have both liquid and solid in between the liquidus and the solidus. If you're having trouble imagining what that might be like, again, go back to the almost frozen popsicle or almost frozen ice cube in an ice cube tray that we did in Module 5. So if you bit into an almost frozen popsicle, it might look solid on the outside, but when you bite in, you then get a lot of liquid because it is partially liquid and partially solid. And that's the same basic behavior that we're talking about. Now for our particular material, we know our melting point of material A, we saw our melting point of material B, and when we look at our vertical composition line, we can now see where that crosses the liquidus, and that tells us the temperature where our alloy, our 60-40 alloy, would actually begin solidifying if we started off molten and we're cooling it. Where the vertical composition line crosses the solidus, that actually then tells us the final temperature. As long as we cool and lower below this temperature, then our entire alloy should be solid. But in between those two temperatures, we're going to be both liquid and solid. These 2 points, where we begin solidifying and where we finish solidifying, they're both at temperatures lower than B's melting point, but they're both at higher temperatures than A's melting point. So by alloying, we can actually control the melting point behavior, and sometimes we really want to do that. Now, often it's important to note exactly what state we're at a given temperature. So we're going to do for our 40-60 example, we're going to consider that we're at some known temperature T1 that's been given. Maybe it's 100 degrees Celsius. So we can draw a horizontal line that shows the temperature that we're currently at for our vertical composition, and where those 2 lines cross, we're going to call the state point. And the state point just tells us, are we all liquid, are we all solid? But we see our state point falls below the liquidus and above the solidus, so we're actually in a liquid and solid state. And so now it gets really interesting because we don't know what percent of the material is liquid and what percent of the material is solid. We also don't know of that liquid how much of it is A and how much of it is B, and then how much of the solid is B and how much of the solid is A. Now let's pause for a moment. At this temperature, if we were 100% material B, we should be 100% solid because we're below B's melting point. But if we were 100% material A, we should still be 100% liquid because we're above A's melting point. So within our liquid, we might expect to see a little bit more A, and in our solid, we might expect to see a little bit more B, but we don't know. And so what we want to go through now, steps 3 through 6, will actually allow us to determine of the liquid, how much of it is A and how much of it is B, of the solid, how much of it by percent is A and B, and then finally we can actually do a little bit of simple algebra and determine then how much of our total mass is liquid and how much of our total mass is solid. All right, so let's jump in to step 3. So step 3, what we want to do is we're going to find the point where our temperature crosses the liquidus and draw a vertical line. So here's where our temperature line crosses the liquidus. We draw a vertical line, and that line is now indicating the percent of the liquid that is material A and the percent that's material B. And we just look where that vertical line touches our percent weight of A or B axes. So here's the percent of our liquid that is material A, and I would estimate where we're landing there at about 68%, which correspondingly means then that 32% of our liquid must be material B. So shouldn't be surprising there's more of material A in the liquid since material A has a lower melting point. Now step 4 tells us to go ahead and draw a vertical line where the temperature line crosses the solidus. So there's our point. We'll draw our vertical line, and then we can get the percent of the solid that's material A, and I would estimate that to be at about 17%. And so the percent of the solid that's material B is 83%. So more B has solidified than A. And so here's our final percentages that we found and the finished diagram with our vertical lines and our temperature lines that allow us to then determine the percent of each material in the liquid and the percent of each material in the solid. Now, if you're concerned that the solution that you drew is kind of messy and it'll be hard for you to follow to go back and really understand how to find these percents in the liquid and the solid, no worries. Look at page 2 of your handout and you'll actually see the solution is there, so you can continue on practicing steps 1 through 4 to find out what our percentages are, and of course even the percentages that I've estimated off of our horizontal axes are listed as well. But what we haven't done yet is we don't know of the total mass what percent of that mass has solidified and how much is still liquid if we're cooling. And so we want to do an additional example. You can see it listed here, and this is on your handout. So if we have 100 grams of this material, how much of that 100 grams is liquid and how much is mass? Now to do this, we want to use 2 equations, and there are mass balance equations. So the first equation, you have them written there in your handout, but the first equation is the very simple, the total mass has to be equal to the mass of the liquid plus the mass of the solid. That's no surprise. The second equation, you're going to use one of the 2 equations listed there. You're either going to use the one for material A or material B. They're the same basic equation. They look confusing. They have all of our percentages on there. But what they're literally saying is that the total mass of A has to equal to the amount of A that's liquid plus the mass of A that's solid. Or the total mass of B is equal to the mass of B that's liquid plus the mass of B that's solid. So that's also not a surprise. It's basically still equation 1, but just broken out just for material A or B. So you'll use equation 1 and then either equation 2 for material A or equation 2 for material B, because we'll have 2 unknowns, the mass of the liquid and the mass of the solid, and we need 2 equations for 2 unknowns. Let's see what that looks like. Feel free to be writing it out on your own. So again, here's our example problem and the equations that we want to use, so we have it all together. And so equation 1, we just said is 100 grams would be equal to the mass of the liquid plus the mass of the solid. And that's going to be the same whether we're writing this with material A's percentages or material B's percentages. But then when we write equation 2, if we're dealing with material A, we have 60% material A, so we need to multiply that by the total mass. And we're going to set that equal to 68% times the mass of the liquid plus 17% times the mass of the solid, because those are the percents of liquid and solid that are material A. Now I have 2 equations and 2 unknowns, the liquid or the solid. So I can do the same thing for material B. For material B, I have 40% of my 100 grams or 40 grams of material B. And then we said 32% of the liquid was material B, so 32% times the mass of the liquid plus our 83% of the mass of the solid. Again, 2 equations, 2 unknowns, so I can either solve the left side or the right side, and I would end up with the same answer, and I should find that the mass of the liquid is 84.3 grams, and the total mass that is solid is only 15.7 grams. Now, of that 15.7 grams, 83% of that is material B. Of that 15.7 grams, only 17% is material A, but vice versa, you have 68% of the 84.3 grams of the liquid is material A. So take some time. Make sure you understand what the percentages are telling you, what these masses of your liquids and solids are telling you. Phase diagrams are tricky to first understand, but once you get the language that they're talking about, they make sense. But you've got to spend a little bit of skull time with them. We will do an example together on Monday in class. It will also be recorded for those of you who are not able to attend. But you want to make sure you get this, because our next topic is actually then getting into partially soluble or insoluble material phase diagrams. And those have additional elements to them. So Get solid here, so make sure you summarize what you just learned, talk to each other, and thanks for watching.